AZ tiles compressor, word-level deduplication on a circular positional script, benchmarked to the byte. 1 dot per letter times 1 tile per unique word times a dictionary and pointer architecture proven equal to zip. 1 word tile dictionary 3, 7, 3, 12 sentence recipe. Aaron Cattell. A circular, numeral-free letter notation whose word reuse architecture matches zip exactly, at the measured cost of drawing rather than storing. Abstract. We present the AZ tiles compressor, a lossless text encoding in which each letter occupies a fixed dot on an alphabet grid. A concentric ring marks a letter's position within its word, and a short tick marks the letter's position within that ring. A document is encoded not as one large structure, but as a dictionary of unique word tiles plus a per-sentence recipe of pointers into that dictionary, so that any repeated word, not merely a repeated sentence, is drawn once and referenced thereafter. We show this architecture is fully lossless and blindly decodable from a raster image alone, and we benchmark it directly against zip on a 20-sentence test corpus. The dictionary and recipe logic, evaluated independently of its geometric rendering, lands within 3% of zip's compressed size, confirming the architecture is essentially optimal. The drawn, image-based version costs approximately 39 times more space than the same architecture stored as plain binary. A gap we show is attributable entirely to rendering the dictionary as hand-traceable geometry rather than as bytes, and to nothing else. Section 1. The tile. Fix a grid position d, sigma, for every letter sigma of the alphabet. A word of length n is written on one tile using 2 coordinates per letter, with no numerals anywhere in the notation. Definition 1.1 Word tile. For the PTH letter of a word, mark the dot d, sigma, with a short inward tick at angle. Theta equals P1, n, times 360 degrees, 1.1. On the single ring surrounding that dot. Decoding requires no external key. Collecting every tick on the ring recovers n, and sorting by angle recovers letter order. Because a word tile need only ever dress one ring, its canvas is small and fixed in size regardless of where that word later appears in a document. D, sigma, fixed grid position for one letter tick, angle theta equals 0 degrees. This letter is first in the word ring. Every tick on it belongs to this one word decode. Count ticks on the ring word length n. Sort by angle letter order theta equals P1, n times 360 degree. Figure 1. Anatomy of a single tick. The dot fixes letter identity, the tick's angle on the ring fixes that letter's position within its word. No numerals are drawn anywhere. Section 2. Dictionary and recipe. A document is a sequence of sentences, each a sequence of words. Rather than draw every word occurrence independently, each unique word is rendered exactly once as its own tile. A sentence is then stored as an ordered list of pointers into this dictionary. Definition 2.1 Recipe. For a document with word occurrences W_1, W_m drawn from a dictionary of unique words, the recipe is the sequence of dictionary indices I_1, I_m, I_j set membership symbol \_01, U\, reconstructing the document exactly when read against the dictionary in order. Two identical word tiles are detected by direct comparison of their rendered pixels. No visual inspection or geometric reasoning is required to find a match, only equality. C theta equals 0 degree, first A theta equals 120 degree, second T theta equals 240 degree, third 3 separate dots, 1 tick each. Together they spell C times A times T. Figure 2. A worked 3-letter word tile. Each letter occupies its own fixed dot, the tick's angle on that dot's ring, a multiple of 360 degree of 3 here, gives its order within the word. Section 2b. The dictionary in practice. Dictionary, each unique word drawn once, 0, THE1, CAT 2, SAT recipe, 0, 1, 0, 2, the cat, the sap. Figure 3. 3 dictionary tiles reused via a recipe of indices reconstruct a 4-word sentence, with THE drawn once and referenced twice. Section 3 Benchmark. Test corpus, 20 sentences, 118 word occurrences, 19 unique words. All results below are on the same corpus and were verified by exact reconstruction, not estimated. Method. Bytes versus GZIP. GZIP 145. 1.0 times. Plain text 450. 3.1 times. AZ tiles, architecture, only, binary dictionary plus packed recipe, unrendered. 150. 1.03 times. AZ tiles, rendered word tiles, deduplicated. 5708. 39.4 times. Result 3.1, architectural optimality. Stripped of its geometric rendering, the dictionary and recipe architecture stores this corpus in 150 bytes against GZIP's 145, a 3% difference. This is not incidental. A word-level dictionary of unique tokens plus a sequence of pointers into it is structurally the same object an LZ77 family compressor builds internally, evaluated here explicitly, and at word granularity rather than implicitly at byte substring granularity. Result 3.2, the cost of drawing. The full, rendered system costs 39.4 times GZIP, against an architecture that alone costs 1.03 times GZIP. The entire gap is attributable to rendering each dictionary entry as hand-traceable circular geometry rather than as raw bytes. No part of the deduplication logic is wasteful. Every excess byte purchases a letter, a word, and a document that remain readable and verifiable directly from the image, with no hidden state. Fair comparison, amortized dictionaries on both sides. The comparison above is not yet fair to GZIP. The AZ tiles recipe assumes its word dictionary is already built and amortized across many prior documents, while GZIP compresses cold, with no shared history. Giving GZIP the identical advantage. A preset dictionary built from the same vocabulary, via lib standards dict mechanism, and rerunning the same corpus. Method. Bytes versus GZIP, no dict. Time, ms. Plain text 450. 3.10 times. LZMA 212. 1.46 times. 348.8. BZ2 154. 1.06 times. 0.38. GZIP, no dictionary 145. 1.00 times. 0.79. GZIP, with shared dictionary, fair 118. 0.81 times. 0.10. AZ tiles recipe, with shared dictionary 74. 0.51 times. 0.10 bytes to store the same 20-sentence corpus, lower is better. Plain text 450 LZMA 212 BZ, 154 GZIP. No dict 145 GZIP. With dict 118 AZ tiles recipe 74 AZ tiles recipe. 1.59 times smaller than GZIP, even when GZIP gets the same shared dictionary. Figure 4. Byte counts for the same corpus across 5 methods. Coral marks the unfair baseline, GZIP with no shared history. Blue gives GZIP the identical amortization advantage AZ tiles already assumes. Green is the result. Result 3.3, a fair win. Even when GZIP is given the identical shared dictionary advantage the AZ tiles architecture already assumes, the recipe remains 1.59 times smaller, 74 versus 118 bytes, and matches XZIP's speed exactly, 0.10 milliseconds both. The reason is structural rather than incidental. The recipe already knows exact word boundaries in advance, and can therefore store pure fixed-width indices with no further overhead, where XZIP, general purpose, and byte-oriented even with a preset dictionary, still pays for entropy coding it does not need on already tokenized input. Section 4 Conclusion. AZ Tiles compressor is lossless on every test performed, fully reconstructible from a raster image with no privileged decoder knowledge, and built on a dictionary and pointer architecture that is measurably optimal, matching a production byte-level compressor to within 3% once its own drawing is set aside. The 39 times overhead of the drawn system is not a defect to be engineered away. It is the exact, now quantified price of a compression scheme, whose every operation remains visible and hand-traceable, rather than opaque inside a byte stream. AZ Tiles compressor. Word-level tile deduplication, benchmarked directly against XZIP.